Welcome to part 2 in our series of videos on the drying of fruits and vegetables. In this session, we will look at the methods of drying. My name is Don Mercer and I am with the Department of Food Science at the Ontario Agricultural College, University of Guelph. We will begin with several acknowledgements and then I would like to go over some introductory observations. We'll look at methods of drying and then examine the basic dryer design and operation. We'll look at key factors in drying and then methods of achieving proper drying conditions. Once we have done all this, we will wrap things up with some summary comments. I would like to thank Mr. Andrew Goodwin, Associate Industrial Development Expert with the Agribusiness Development Branch of the United Nations Industrial Development Organization, for his considerable efforts in coordinating this project. I would also like to thank those who are assisting in the presentation of this material to various local groups. Their contributions to our training activities are greatly appreciated. Having worked with industrial food dryers, as well as building and using various types of dryers, there are some general observations that I would like to share with you before we actually begin looking at the ways in which we can dry food materials. Food drying is something that a lot of people think they can do. However, very few people seem to take the time to learn enough about drying to understand it and do it well. Many of the things that you need to understand in order to dry food materials are things you already know from your everyday life. These are acquired skills and knowledge. You just have to know how to translate this knowledge to a food drying process. So that's the application of these skills and knowledge. Any of you who have ever dried a load of laundry probably already know the basics of drying technology. Let's consider this sock, which is laid out flat, and compare it to the one here, which is rolled into a ball. If both of these are wet and we place them into a dryer, which do you think will dry better? And of course the choice is obvious. Remember to apply this type of knowledge and logic as you dry food materials. In addition, many of the things that affect cooking food and getting heat into them can also be applied to getting moisture out of them. In this case, consider the yam on the left. If we wanted to cook this yam, we would not cook it in its whole form. We would cut it up into slices and cook it that way, because we know that the slice will cook much more efficiently than the large piece on the left. So please keep this in mind as you think about drying. Sliced products will tend to dry better than large pieces of product. Now let's take a look at methods of drying. Most drying requires the application of heat to evaporate water from the material. We begin with water in its liquid state, and through the addition of heat, what we do is convert that water into its vapor state, which can then be removed from the dryer by currents of air. Some drying methods use a different approach, and we will discuss these a bit later on in our presentations. Heat can be applied directly, as in the case of drying material over an open fire, where the heat comes directly from the flames and often impinges upon the material, and this is one of the oldest methods of drying. Heat can also be applied indirectly, as is done by heating the air prior to its contacting the material. Here we have a series of gas flames over which we will pass some cool air. The air then becomes warm, and we use this heated air to dry the material as shown on the right-hand side of the diagram, and this then removes the moisture from the surface and carries it away. Indirect application of heat is the most popular and is the one that we will emphasize here. Heat sources include the use of fuels such as the natural gas in the previous slide and solar energy. Solar drying will be covered as an individual topic in this series of presentations. There are numerous dryer designs. Each has been developed to meet the demands of certain products. We will look at two basic types of dryers, which are generally categorized as being continuous or batch. Our focus will be on batch dryers that are suitable for most of our applications. Some dryers are classified as being continuous, as I have already mentioned. Feed material enters at one end of the dryer and is carried through by a conveyor belt or similar device. We can use a simple diagram to illustrate the basic operation of these continuous dryers. We begin with a drying chamber. A conveyor belt will be used to move the material through the drying chamber, and the conveyor belt will move the material from the left to the right, and the belt will return through the bottom part of the dryer and be a continuous loop. Wet feed material is continuously spread on the belt, and it travels through the drying chamber, as you can now see. We will introduce hot, dry air into the bottom of the dryer and blow it upwards through the bed of material, which will then remove moisture. The moist air will then leave the dryer as exhaust air through the stack on the top of the dryer. When it reaches the right end of the conveyor belt, the dry product is continuously removed at this end of the dryer. Continuous dryers are generally large and relatively costly to purchase and to operate. They are used in commercial scale operations where substantial quantities of product are required. Continuous dryers are not suitable for small scale operations such as those most of us will be conducting. Therefore, we will not explore their operation any further. Batch dryers are much more appropriate for the needs of small-scale operations. As the name implies, when using these dryers, a batch of material is placed in the dryer and dried until the desired amount of water is removed. Batch dryers for fruits and vegetables are most often a variation of the basic tray dryer design. Once again, we can use a simple diagram to illustrate the basic operation of the dryer. We will begin with the drying chamber. We then have a series of removable mesh trays which are positioned inside the dryer. The material will be spread on these trays and air will be introduced as heated air through the inlet on the bottom left corner of this diagram. The heated air then travels into the drying chamber, and as you can see here, there's a bit of an uneven distribution of the air. Most of it will go across the bottom of the dryer, and very little of it will go to the top of the dryer in this case. We'll remedy this situation momentarily. The air then leaves the dryer through the exhaust air outlet, which is located at the top right-hand side of this diagram. One of the things that we can do to create an even air distribution is to insert air distribution plates into the drying chamber. This creates an area to the left of the air distribution plate where the air will come in, and then the flow will be evened out and it will pass through the holes in the air distribution plate, which I will explain in a few minutes. And then we have this air traveling evenly across the top and bottom surfaces of the material held by these mesh trays. It's also a good idea to add an air distribution plate at the discharge side of the tray dryer as well. This ensures that drying above and below each of the trays in the dryer is kept uniform, and then of course the air will leave through the exhaust air outlet. Here is an example of a lab scale tray dryer that I built to test some concepts for the drying of mangoes. At the bottom left of the photograph we have heater fans which blow warm air through these pipes into the air inlets in the drying chamber or drying cabinet. And as you can see here, we have a number of trays in the dryer, and I have a plexiglass door on it so I can watch what happens in the case of this lab scale dryer. You can't see it, but on the far end, hidden from view, are the air outlets where the exhaust air will leave and go into the surrounding area of the room. Here's a pilot scale dryer that was built in Malawi, and it's an upscaled version of the one in the previous slide. It's simply made from sheets of plywood, and you can see that inside it has 2 banks of 6 trays each, upon which the material to be dried can be placed. Commercial tray dryers are also available on a smaller scale for home use, and here we see a small Nesco dryer which uses circular plastic trays which are stacked one on top of the other, and the material is placed on these trays, and the temperature of the air which blows through the dryer can be adjusted to suit your various needs. Another type of home tray dryer is the Excalibur dryer, which consists of 9 square trays in a cabinet. The photograph on the left is a little bit hard to see because the panel is on the front of the dryer, but if we remove this cover you can see the 9 trays inside the dryer, and in this case the air blows from a heater fan in the back towards the front and escapes from the drying chamber through a set of vents in that front cover. So what are the key factors in drying? There are several key aspects in drying food materials that we need to keep in mind. Preparation of the material itself is so important that we're going to cover it as a separate topic. We'll look specifically at mangoes as well as tomatoes and several others. But spreading of the material on the drying racks must be uniform. Pieces of material should not touch each other or overlap on top of each other. And in this set of diagrams, we can see that the 2 shapes on the bottom left are touching each other at their edges. The 2 shapes on the right are overlapping, and the points of contact are potential problem spots. If they're touching at the edges, that's not so serious of a problem if the material shrinks as it's drying, because then these areas of contact will pull away from each other. But in the case of overlapping, the overlapped area will not dry, and that creates an area of uneven moisture in the product, and that can lead to problems later with spoilage and things like that. All pieces should be of uniform thickness, and again we'll look at that later when we study the preparation of our materials for drying. Using these simple diagrams we can show how water loss can occur. In the case of the figure on the left, water leaving from the center of the material will have a shorter distance to travel to the surface where it's evaporated than it will from the center of the figure on the right. Water has further to travel to reach the surface from the middle of thicker slices than it does for thinner slices. Thinner slices will tend to dry faster because of this. The temperature of the air should be suitable for drying, and again we're going to look at this later on as well. But 50 to 55 degrees Celsius is just about right for most fruits and vegetables. Higher temperatures can reduce quality and create problems. So try to limit your drying temperatures to about 55 degrees maximum, and if you work between 50 degrees and 55 degrees Celsius, you shouldn't have any problems. The distribution of the air in the dryer needs to be uniform across the material being dried. Areas receiving poor airflow tend to dry slower than those experiencing an adequate amount of air exchange. So we'll take some mesh here and place 4 pieces of product on it. Under the 2 pieces on the left, we will give them a high rate of airflow. Under the 2 pieces on the right, we will give it a lower amount of airflow. And what will happen is we will get better drying with adequate airflow in the figures on the left than we do with the figures on the right, where we will get poorer drying with the low level of airflow. The velocity of the air must be sufficient to remove moist air from the surface of the material being dried, and we're also going to look at this later on as well. But here we have some material with a layer of moisture on the surface. We will blow air at a sufficient rate across the surface so that we can remove the moist air which is in contact with that moist surface of the material, and that will sweep away the moist air from the surface and replace it with warm, dry air that will lead to further evaporation. If we have a similar set of conditions, but we use a lower airflow rate, the air might not be able to disrupt that surface condition, and the moist air will stay in contact with the surface of the material, and drying will not be proceeding as we want it to. So stronger airflow can disrupt moist air at the surface better than weak airflow. The direction of airflow must also be considered when designing a batch dryer. The diagram on the next slide will help illustrate this point. There are several options for airflow directions. We can have vertical airflow upward onto the material surfaces, and we can look at that in this diagram. So here we have the material that's going to be dried, and we have air coming from the bottom in an upward direction. This tends to dry the bottom surfaces of the material. We can also use downward airflow onto the surfaces, as shown by this arrow, but this tends to dry only the top surfaces, or dry the top surfaces first. Then we also have the option of horizontal airflow across the material surfaces. So in this case, we're going to bring the heated air across the top surface of the material and across its bottom surface. And this will work well to dry both the top and bottom surfaces of the material. And that's what we should be striving to accomplish. A suitable period of time must be allowed for the removal of moisture from the material being dried. And again, we will look at this material later on as well. You need to keep in mind that you really cannot rush the drying process. Attempting to do this will result in failure. So how do we achieve proper drying conditions? Part of the challenge in obtaining the proper drying conditions is understanding how to design your dryer to meet the needs of the materials you are trying to dry. Fortunately for us, most of the fruits and vegetables that we will be drying are usually dried in the form of slices. A common misconception, however, is that heat is the only thing you need in order to dry most things. Some people try to use temperatures as high as 80 degrees Celsius and meet with problems, so avoid these excessively high temperatures. Heat is only part of the overall drying system, but we do need to understand how we can deliver heat to the material in the dryer. The air itself can be heated by passing it over the coils of an electric heating unit if this is an option. A fan will be needed to move the air across the heating coils and into or through the drying chamber. In this photograph, you see a fan at the inlet to a dryer. This fan will blow air into the chamber where the electric heaters are located, and then that air will go on into the drying chamber where it will remove the moisture from the material to be dried and then leave the drying chamber through exhaust vents. In this case, we have a fan at the outlet of the dryer which will assist in the airflow, and this fan is actually designed to pull air from the drying chamber and exhaust it to the surrounding environment. When fuels such as natural gas are available, air can be passed through a heating chamber similar to that used in various furnaces. So what we have here is a heating chamber with a natural gas element in the bottom. When the natural gas is ignited, we get a nice blue flame, and we can bring cool air into the heating chamber, pass it over the flame, and we end up with heated air that has a high drying capacity that can be used to remove moisture from products in the drying chamber. This is often not a viable option since natural gas may not always be available. In solar drying, air can be passed through a series of metal tubes or ducts to be warmed up. Painting the metal surfaces black and exposing them to the direct rays of the sun will aid in achieving the desired drying temperatures. And here we have a photograph of a homemade solar dryer that I was working with in our yard at home. The drying chamber is shown here at the top portion of the photograph. What I really want to point out is the heat collector, which consists of a sheet of metal over a channel through which air passes, and as the air travels upward through here, the heat from the metal warms that air. By painting the metal black, it gets so hot that you cannot even hold your hand on it for any length of time without the risk of burning your skin. Solar drying will be discussed in a separate video devoted to this topic, and here's another homemade solar dryer that I used in Equatorial Guinea. To achieve proper contact between the heated air and the material being dried, you should have both the top and bottom surfaces exposed to the air. This can be done using wire mesh with a reasonably open weave. The opening size must not allow the product to fall through it. Only mesh made from materials which are safe to contact foods should be used. While galvanized metal chicken wire may be suitable for testing the design of a dryer, it should not be used for actual food drying applications because galvanized metal is not a recognized safe contact surface for foods. Although it is more costly, stainless steel is best, but plastic mesh may work just as well. In this photograph, we see plantain slices on a stainless wire mesh in a dryer in the lab. And in this photograph, we see the tray from the Nesco dryer, which you saw a few slides ago. Obtaining a uniform distribution of air within the dryer is a problem we all face. Using air distribution plates can be a solution to this problem if there is sufficiently high airflow. Air distribution plates are panels in the dryer that are designed with a series of holes or slots, and we've already mentioned these in the case of the design of a tray dryer. And here you can see what the design looks like. It's actually nothing much more than a sheet of metal with holes drilled at regular intervals in it, and this will then be inserted in the dryer to aid in evening out the distribution of air. Incoming air usually has a very chaotic pattern of flow. It strikes the air distribution plates and is partially obstructed from reaching the material in the drying chamber. This creates back pressure. The back pressure then forces the air through the holes or slots, which now act like nozzles, injecting the air into the drying chamber in a uniform manner. So let's take a look at a dryer with and without air distribution plates. We take this drying chamber and we put the bed of material in there as indicated by this blue area, and then we will bring heated air into the bottom portion of the drying chamber below the bed of material. The air will travel across the bottom of the dryer and probably strike the right side of the dryer, and then we will get a chaotic airflow pattern. Because this airflow is so chaotic, we will get an uneven distribution of air going upwards through the bed of material. And I've indicated that here by the differences in the arrows on the right hand and left hand side of the diagram. So the area on the right hand side of the diagram is getting a higher flow of air than that on the left hand side of the diagram, and what will result is uneven drying. This air will then leave through the exhaust air stack at the top of the dryer. Now what we want to do is remedy the situation through the use of an air distribution plate. So once again we will start with the drying chamber and have the bed of material in place. we're going to insert an air distribution plate below the bed of material, between the bed of material and the inlet of the heated air. So the air will come in, and once again we will get this chaotic airflow pattern. But because of all the small holes and the back pressure that we've created, we will get a uniform flow of air through the holes in the air distribution plate, and that even airflow will pass up through the bed of material and give us even or uniform drying. And once again, that air will leave the dryer through the exhaust air stack. There is a limit to how much water can be evaporated into the air passing through a dryer. Keep this in mind and don't try to remove excessive amounts of water with only low flows of air. This is a more common problem than you might think. It's better to have a set of smaller trays in a stacked arrangement in a tray dryer than having a single long tray over which the air is passing. By the time the air reaches the end of the long tray, it may have become saturated with water, which makes it unable to pick up any more water on its travels. Here we have the stacked tray arrangement in the tray dryer, which you have already seen. In this case, we will have a long single tray arrangement in a fixed bed tray dryer. We'll put the bed of material here, we'll bring the heated air in one end and pass it through an air distribution plate, and as it progresses along the length of the dryer, it will pick up moisture and eventually leave the dryer through the exhaust air vent. However, it will have good water removal capacity as it enters the dryer, but because it's picking up more and more moisture, it will lose its ability to pick up moisture, and you will end up with poor water removal capacity towards the discharge end of the dryer. As a result, the material at the end of the dryer will remain wet after the material at the point where the air is entering is already dry. So in summary, we have briefly examined the basic methods of drying and have discussed the key factors involved. Although most of you will not have the opportunity to design your own dryers, it is important to understand the basic design concepts in order to make effective use of the dryers which are available to you. In future presentations, we will examine how drying actually takes place, as well as the effects of drying on the product, and we will look at how to prepare materials for drying. Once we have covered these points, we will be in a position to examine the drying of mangoes and tomatoes, as well as looking at solar drying. Thank you very much.